Let's talk about how we would compute a determinant which is bigger than 3 by 3, because all the examples we've done so far are 2 by 2 or 3 by 3. So we have this 4 by 4 matrix here, and the determinant of A, our 4 by 4 matrix, has 24 terms because 4 factorial is 24. Now there's two reasonable ways to do this, and I've drawn pictures of them. So we could take the entries in the first row one at a time and take the entry in the first row, first column, and then the determinant of the 3 by 3 matrix that we get by eliminating that row and column, minus the next entry over, times the determinant of the matrix we get by eliminating that row and column, plus the next row over, times the determinant of the submatrix we get by eliminating that row and column, minus that last element in the first row, times the determinant of the matrix we get by eliminating that row and column. So the signs alternate, plus, minus, plus, minus. That's called expanding on the first row. And there's a similar rule for expanding on the first column. We look at the entries in the first column one at a time and give them alternating signs, plus, minus, and we multiply each one by the submatrix we get by eliminating the row and column containing that first element. So eliminating row 1, column 1, or row 2 in column 1, or row 3 in column 1, or row 4 in column 1. Again, that's called expanding on the first column. So let's do one example of this. Well, actually first, let me do some notation. So this is the 4 by 4 case. How would I explain this in the n by n case? So I have to somehow capture the pluses and minuses and the correct determinants. So let's define capital Cij, which we'll call the ij cofactor of a matrix to be -1 to the I plus j times determinant of the submatrix without row I and column j. So that's what I'm trying to capture in red here, and the sign before each matrix. So if A is an n by n matrix, the determinant of A is, if we use the row method, A11 C11 plus A12 C12, etc., up to A1n C1n. And then if we use the column method, it's A11 C11 plus A21, so going down, C21 plus, etc., up to AN1 CN1. So those are the two important formulas for determinants of a matrix, that's especially if it's large, because the only matrices I can really do in my head take the determinants of are the 2 by 2 and 3 by 3 matrices, unless they happen to be upper triangular or lower triangular, or if they have a row of zeros or one of the other properties that makes me know that their determinant is something easy. Alright, so now that I've stated this formula in general, let's try this on a 4 by 4 matrix with numbers. let's compute the determinant of the matrix 1, -2, 1, 1, 2, 1, 6, 2, 0, 3, 1, 0, 0, 2, 12, 4. So this is a 4 by 4 matrix, so I can't just draw diagonal lines like I would for a 2 by 2 or a 3 by 3. So I can either write out a sum of 4 determinants of 3 by 3 submatrices and multiply them by the entries in the first row, or I could do the first column. Now since there's 2 zeros in the first column, I think that's a good strategy, because it's going to be 1 times something minus 2 times something plus 0 plus 0, because 0 times anything is 0. So let's take advantage of those zeros and expand this determinant on the first column. So this is 1 times determinant of, so we'll cross out the first row and column, and we've got 1, 6, 2, 3, 1, 0, 2, 12, 4. That's something that I could do with diagonal lines. Minus 2 times the determinant of, so we'll get rid of the row and column containing that 2, -2, 1, 1, 3, 1, 0, 2, 12, 4. Alright, now, so let's look at this determinant. Now we could compute that by diagonal lines, but I see something fishy there. That third row looks a lot like the first row. It's 2 times the first row. And if we ever have a matrix where there's one row that's equal to a multiple of another row, then that determinant is 0. So it's not worth actually computing it. We can just see, because this row is a multiple of the first row, that it must be 0. So that's 1 times 0 minus 2 times, I don't see that going on in this matrix, so let's do this out. And that last column is 1, 0, 4. Let me write it a little further over, because that I don't want that 12 to run into it. There we go. So we've got -2 times 1 times 4, which is -8, plus 0 plus 3 times 12, minus 2, minus 0, minus 12. So that's -2 times what's in the parentheses. 3 times 12 minus 12 is 2 times 12, so that's 24 minus 10 is 14. So minus 2 times 14, so I guess the determinant is minus 28. The end.